All right, let's dive in. Similar to what we did on Tuesday with our quadrilaterals, we're going to sort of start by giving some definitions, the characteristics, the properties of different types of triangles. There are different types of triangles, and we can describe those triangles using these terms. The first triangle we're looking at here is called an equilateral triangle. And in an equilateral triangle, all the sides are equal and all the angles are equal. So all three sides are the same length and all three angles have the same measure. Does anybody remember what the sum of the angles of a triangle would be? If you add up the three angles in a triangle, does anybody remember what those add up to? You don't have to. It's just one of those things that you might remember from geometry somewhere along the way, that the three angles in a triangle add up to a certain number. All right, nobody. All right, well, that's okay. The three angles of a triangle add up to 180 degrees. That might sound familiar after we say it. What that tells us then is in an equilateral triangle, since every one of these angles is equal, what is the measure of each angle in that equilateral triangle? What's the measure of each one of those angles? If they add up to 180 and they all have to be the same, what's the measure of each one? And you can either turn your microphone on or you can type in the chat. Either one of those is just fine. Okay, Kebra, Jessica, Ashley's got 60, Jenny's got 90. Let's take a look. If we have three of them and they're all the same, we have 180 divided by 3. Each one of them is going to be 60 degrees. That's right. So each one of those angles is going to be 60 degrees. In an equilateral triangle. Next type of triangle we'll look at is called isosceles. I always wanted to name a dog isosceles. I've never been able to get my family to get on board with that. That's okay. An isosceles triangle has at least two sides that are equal, at least being very important. The words exactly and at least are very different from each other. On Tuesday, we talked about the fact that a trapezoid has exactly two pairs of parallel sides. Exactly means what it sounds like, exactly. Or excuse me, exactly one pair of opposite sides are parallel in a trapezoid. Exactly one pair, no more, no less. Here, it's at least two sides are equal. Now, in the triangle we have drawn here, we can see that those are the sides that are equal to each other. And so at least two sides are equal in an isosceles triangle. The third type of triangle we're going to look at is called scalene. And in a scalene triangle, no sides are the same length, no angles are equal. And so essentially what we've got here is we've talked about the side lengths of a triangle. We have no sides that are the same as each other. We have at least two sides that are the same as each other. And we have all three sides are the same as each other. Those are three different descriptions of triangles we can use that are all about the side lengths. All of these names are about the side lengths of the triangle. And that's how we describe them as scalene, isosceles, or equilateral. Down at the bottom, we've talked about side lengths. Now we're going to talk about angles. So in a right triangle, one of the angles measures 90 degrees. And we can see that with that little symbol there in the corner, that little square indicating that it's a 90-degree angle. I have a question for you. Would it be possible for a triangle to have two 90-degree angles in it? Would it be possible for a triangle to have two 90-degree angles in it? Okay, Jenny says no. And I guess my question, my follow-up, and anybody can answer, it doesn't have to be Jenny, why not? Nice, Matthew. I like it. Why wouldn't it be able to have two 90-degree angles? And there's a couple of different ways you can go about this, and we'll talk about them both. Might not be the easiest thing to put into words, so you kind of do your best there if you're typing, and I'll kind of take a look at what you've said. Okay, so we've got a yes, and we can form a rectangle from Laura. That's an interesting one. I'm going to hold on to that one for a little bit here. So if we had two 90-degree angles in our triangle, we could form a rectangle. I agree with that, Laura. I agree with that part of it. I agree with the second part of what you said there with the we can form a rectangle. So let's see here. If I try to make a triangle with two 90-degree angles in it, so make it a triangle. I've got a 90-degree angle there. Okay, I could make a triangle out of this thing. If I make another 90-degree angle over here, while it's true, Laura, we can make a rectangle out of that. I don't think we can make a triangle out of it because I've got too many sides. If I've got a 90-degree angle over here and a 90-degree angle over here, I can't make a triangle out of this. You're exactly right. I can finish it off and make a rectangle, but what happens is once I have two 90-degree angles, now I can't have a triangle anymore. Another way to think of this is we know if you add up all the angles in a triangle, it's 180 degrees. If my first angle is 90 and my second angle is 90, I'm already at 180. There aren't any degrees left for my third angle. So no, I can't have two 90-degree angles in one triangle. That's why when we describe a right triangle, we're saying that one of the angles is 90 degrees. You can't have any more than that. All right, well, we could have a 90-degree angle. We could have all the angles be less than 90. And if that happens, we call it an acute triangle. All the angles are less than 90 degrees. They're all smaller than 90 degrees. Now that picture there happens to be the same as our isosceles triangle, and that's okay. That's just an acute isosceles triangle. But all the angle measures are less than 90 degrees. We call that an acute triangle. Still talking about our angle measures here, we can have one that's 90, we can have all of them that are less than 90, and then the third case is we can have an obtuse triangle where one of them is greater than 90 degrees. Here, that's this one. It's bigger than 90 degrees. When we have one angle that's bigger than 90 degrees, we have an obtuse triangle. We can only have one that's bigger than 90, because if I had a 91 and a 91, that's too many degrees. It can only have 180 total, so two 91s would be too much. So we can only have one obtuse angle in there, and that makes it an obtuse triangle. We can describe triangles with side lengths. We can also describe them with angle measures. With side lengths, we have scalene, isosceles, and equilateral. With angle measures, we have right, acute, and obtuse. And these can be used in conjunction with each other. You can use them both. You could have a isosceles acute triangle. In fact, we have one of those on this page. We have one right here, an isosceles acute triangle. Most importantly, it's you will need to know those definitions. And then just like we did with our quadrilaterals, we're going to extend this into true-false questions about these properties and definitions. Let's look at a couple. Some true-false questions, just like we did on Tuesday. Every equilateral triangle is isosceles. And then the second one, all acute triangles are equilateral. I'm going to set up a poll for this one and give you a chance to try it. So the first answer in the poll corresponds to the top question on the page. The second answer in the poll corresponds to the bottom question on the page. You should see 4 choices, and you choose the one that corresponds with what you think the correct answer is. Every equilateral triangle is isosceles, and then all acute triangles are equilateral. Like we talked about on Tuesday, you hear true, false, and you think, well, how hard could it possibly be? Well, sometimes, especially with these definitions, true, false questions can be a little challenging. Remember, our approach to these is try to find a counterexample. Can you find one example that shows it false? If you can find one example that shows it false, then it's false. In your effort to find an example to show it false, you may convince yourself that it's true, and that's perfect. That's exactly what we're after. If we can convince ourselves that, hey, this must be true, then great. Then we can answer true. We're not going to prove it. We're not going to do a two-column proof or anything like that. What we're going to do, though, is we're going to go through the steps of trying to show it false. If we can find one counterexample, then great, it's false. If we can't, then we've kind of convinced ourselves, you know what, this thing must be true. We'll go another 15 seconds on this and then talk about it together. See how we're doing here. Okay, most common is true, false. Up next is false, false, and then a little bit for true, true. Let's go ahead and take a look at these and we'll talk through them. I think the first one here is pretty challenging, actually. Every equilateral triangle is isosceles. Remember, our approach is to try to find one counterexample. What that is if I can find one example of this being false, then I say it's false. Because in math, for it to be true, it has to be true all the time. One counterexample wrecks it. It's no longer true. So let's see here. Every equilateral triangle is isosceles. So what I'm going to try to do here, my approach, is to come up with an equilateral triangle that is not isosceles. If I can, then I can say false. So I draw myself an equilateral triangle. Doesn't have to be perfect. Equilateral means all 3 sides are the same length. Isosceles. So this is an important part here. The definition of isosceles is at least 2 sides are the same. Well, here I have all 3 sides are the same. You know what? Sure enough, that's an isosceles triangle. This is isosceles because it has at least 2 sides that are the same length. All right, well, let me try this again. Let me draw a bigger equilateral triangle and see if it still works. So equilateral triangle means all 3 sides are the same length. Now let's see, isosceles means at least 2 sides of the same. Well, you know what? Every time I draw an equilateral triangle, all 3 sides are going to be the same. That means every time I draw an equilateral triangle, at least 2 are going to be the same. So every time I draw an equilateral triangle, it's going to be isosceles. So the statement, every equilateral triangle is isosceles, sure enough, that's true. And the key there is the at least 2 in the isosceles. It's not exactly, it's at least. And so if it has 2 sides the same, it's isosceles. If it has 3 sides the same, it's isosceles. So these equilateral triangles that I drew, they're also isosceles. And every equilateral triangle is also going to be isosceles. Now let's look at the one down there at the bottom. All acute triangles are equilateral. So let's see, if I draw an acute triangle, that means all the angles are less than 90. So that's less than 90, that's less than 90, that's less than, but all acute triangles are equilateral. Well, this isn't equilateral. All 3 side lengths aren't the same here. This one's much shorter than the other 2. So right there is my counterexample, and I can say that this is false. Let me know if you have questions on those. These types of questions can be challenging. Just have to be careful with your definitions. Make sure you know what all the terms mean, and then don't be shy about drawing pictures when you're trying to answer the questions. I think it helps a lot. Something that's not really going to be a point of emphasis in our course, but I do want you to be aware of it, is the triangle inequality. And what that says is, in order for a triangle to be drawn, the sum of any two sides must be larger than the measure of the third side. Now, we can get lost in that language a little bit, so let's hold on a second. The sum of any two sides must be larger than the measure of the third side. Really, what this is saying is if you add up the two short ones, it has to be, longer than the third one, or you won't be able to make a triangle. Here's what I mean. If we tried to draw a triangle with side lengths 2, 4, and 11, and you could try this with a ruler if you want to. I'm just going to sketch, but you could absolutely do this with a ruler to convince yourself that what I'm about to do is accurate. But okay, let's draw it. So I have one that's 2, and then I have one that's 11, and then I have one that's 4. Oh, wait a minute, that 4, it's not going to reach. It's not going to make a triangle. I mean, I could have drawn the 4 this way, but then the 11's out. So 2, 4, and 11 did not work. You could be thinking, yeah, well, you drew it that way on purpose. All right, well, let's try something else then. Let's try it with, if I put the 11 here, and then I say, all right, well, let's do 4 that way. And now I try to do 2, and it's not long enough to reach. What has to happen in order to make a triangle is the two smaller sides have to add up to be longer than the third side. So if I wanted to make a triangle with sides 8, 4, and 11, I could do that because these two add up to be more than this one. But with 2, 4, and 11, I can't. And that's what the triangle inequality says, is the two smaller sides have to add up to be bigger than the third one, or we can't make a triangle. We talked a lot of perimeter and area on Tuesday. We're going to do perimeter and area again today, this time with triangles. So for perimeter of a triangle, not going to be a big surprise. For perimeter, we're just going to add up the 3 sides on the exterior of the shape. So perimeter, we add up the 3 sides on the 3 sides that are the outside of the shape. For area, though, we're going to need a formula. And here's where our formula is going to come from. If we look at this triangle that we have right here, this triangle that we've marked in red, you know, if we were to take a triangle that's exactly like this one and put it right here. So now I have this blue triangle, and I have this red triangle, and together those make a shape like that. What's that shape called? This shape that's the two of those together? What's that shape called from Tuesday? It could be a rhombus if all 4 are the same length. That's definitely true. We can be certain it's a parallelogram. If all 4 are the same length, we call it a rhombus. I'm not entirely sure that that's true, but what we can say for sure that this is a parallelogram. Let's see, what was the formula for the area of a parallelogram? Anybody remember? Formula for the area of a parallelogram. And if you have to look in your notes, that's okay. The formula for the area of a parallelogram. Base times height. Perfect, Jessica. So the area of a parallelogram is base times height. And if you look here, this triangle that we started with, it's half of that parallelogram. So if we want to find the area of a triangle, if the area of a parallelogram is base times height, then the area of a triangle, which is half of a parallelogram, is going to be 1/2 times base times height. The area of a triangle is going to be 1/2 times the base times the height. So we have that triangle right there. The area would be 1/2 times the base times the height. For the perimeter, we're going to add up all the sides. For the area, it's going to be 1/2 times the base times the height. Let's take a look at one. I want you to find the perimeter and the area of that triangle, keeping in mind that the formula for the area of a triangle is 1/2 times the base times the height. I'll set up a poll for this and let you try it. First answer is perimeter. Yes. Yes, Jenny. For perimeter, well, add up all the sides that are on the outside of the figure. So be careful. We want to add up the outside edges of the shape. Yeah, we don't have a formula for perimeter, but we add up the outside edges. So take your time, find the area and the perimeter of that triangle. Okay, we'll go another 20 seconds and then we'll talk about this one together. See where we are? Okay, not unanimous, but strong agreement here. Let's go ahead and take a look at this one together, and you let me know if you have any questions or if you're not sure where something comes from. So the first thing we're asked to find here is the perimeter. And for the perimeter, we're just going to add up the outside edges. That's it. So that's going to be 12 plus 8 plus 18. Be careful. Because there's a 5 on the screen, we kind of want to include it, but it's not part of the outside edges of my figure. So it's not a part of the perimeter. So our perimeter here is just going to be 12 plus 8 plus 18. We'll add that together and have 38. We weren't given units. We don't know if it's inches or feet or yards or miles. We just know it's 38. And now for the area here is going to be 1/2 times the base, which is the bottom down here, times the height, which is the vertical distance from the top to the bottom. That's where that 5 is going to come into play for us. So it's going to be 1/2 times the 18 times the 5. So 1/2 times 18 times 5. And you can just multiply those in a straight line on your calculator. You can just go 1/2. Oh yeah, we should talk about that. Well, how do I get 1/2 on my calculator? A fraction like that, that 1/2, 1/2. Really, that's just 1 divided by 2. So we'll start out this problem by doing 1 divided by 2, and that'll give us 0.5 on our calculator. So we'll have that 0.5 that we're going to multiply by 18 and then multiply by 5. But 1/2 as a fraction really just means 1 divided by 2. So we'll start with that. 1 divided by 2 gives us the 0.5. Then we'll multiply by 18, multiply by 5, and we end up with an area of 45. So our perimeter here is 38. Our area is 45. Let me know if you have any questions about anything we did there before we go forward. Very good, Matthew. That's awesome. So we looked at properties of triangles and definitions related to triangles, and now we've looked at perimeter and area of triangles. There's some other problems with triangles that we can solve. Not sure I understand the question, Jenny. We might have to stick with that one for a little while. I'm not sure I know what you mean by single numbers. Okay. It's true that we're using the 18. That's our base. So that's what we plug in for B when we find the area. And the 5 is our height. So that's what we plug in for the height. So when we use the formula for the area, we took the 18 and we plugged it in for the base, and we took 5 and we plugged it in for the height. And then when we multiply these together, the 1/2 becomes 0.5, and we'll multiply by 18. And if you want to see it in more detail, we can. You could do, once you've done 0.5 times 18, you'd have 9, and we're going to multiply that by 5, and then end up with 45. If you wanted to do it with fractions instead of decimals, you absolutely could. I think you're going to be allowed to have a calculator all the time. So if you want to do it with this way, that's fine. If you want to do it with fractions, you're right, Jenny. We'd do 1/2. We'd write 18 as a fraction. We'd write 5 as a fraction. And then we could multiply across the top, and we get 1 times 18 times 5 is 90. 2 times 1 times 1 is 2, and then divide at the end to get 45. But you're going to be allowed to use a calculator all the time. Quizzes, exams, all the time. We will get very comfortable with decimals throughout the course. Hopefully that clears that up. Okay, we did properties definitions. Now we've looked at perimeter and area. There are some other types of problems we can solve that involve triangles. Before that, I want to do a little bit of a review with you on proportions. Proportions is when we have one fraction equal to another fraction, and if we know 3 of the 4 pieces, we can find a missing piece. This will probably look familiar to you, but you let me know if you have any questions. A proportion is when we have one fraction, like 2/9, equal to another fraction, like x over 15. And in this structure here, I have one fraction equal to another fraction. And I know 3 of the 4 pieces. I'm trying to find a missing piece. That's what we put the x there for. We don't know what goes there yet. That's what we're going to find out. So this is a proportion. And to solve this, we use a technique called cross multiplying. When we have a setup like this, we use what's called cross multiplying. And we multiply this way, and we multiply that way. When we multiply here and we get x times 9, that just gives us 9x. You could write it as x times 9, but 9x is a little more advanced way to write it, a little simpler way to write it. Multiplying 9 by x is 9x. And then the other side, we have 2 times 15, that's 30. And those are equal to each other. So when we cross multiply, what we end up with is we take one fraction equal to another fraction, we cross multiply, and now we have an equation that we can solve. 9 times x equals 30. I have multiplication here, 9 times x. I want multiplication to go away. When I'm solving this, I'm trying to get this x by itself. When we see solve an equation, that's what we're doing, is we're trying to get x by itself. Now, to be honest, we won't do a ton of algebra in this class, but it will come up from time to time. And when it does, we'll do some review to try to make sure you're comfortable. But here, we're trying to get this x by itself, which means we want the 9 to go away. This is 9 times x, so I want multiplication to go away, so I'm going to divide by 9. When I do that, those 9s are going to cancel, leaving just the x on the left-hand side of the equation. Key is, if I divide by 9 on the left-hand side of equals, I also have to divide by 9 on the right-hand side of equals. Whatever I do to one side, I have to do to the other to keep things equal. They were equal when we started. We want to keep them that way. And so now we'll do 30 divided by 9. And when we do that, 30 divided by 9, I get 3.3333. And that just keeps going on forever. This particular problem told me to round my answer to the nearest hundredth. So that's what we'll do. Rounding is going to be really important for us. We talked about it a lot on Tuesday, and here it comes. Round this to the nearest hundredth. So the first thing I do is find the hundredths place. That's 2 past the decimal. Then I'm either going to round this up or down. To figure that out, I look one space to the right. If the number in that position is 5 or higher, I'm going to round this up to 3.34. If it's 4 or lower, I'm going to round it down. Since in this case I have a 3 in that spot, it's 4 or lower, I'm going to round this down. And my solution to this proportion is going to be 3.33. Let me know if you have any questions on that before we start looking at questions where we're going to use proportions to solve them. All right. Similar triangles. 2 triangles are considered to be similar if they have the same shape but a different size. So kind of like if you put it through the copy machine at 60% and it came out smaller, or 121% and it came out bigger. They have the same shape but different size. And you can look at these triangles here, triangle ABC and triangle DEF. They have the same shape, they're just different sizes. That makes them similar triangles. They're not exactly the same, but they're similar because they have the same shape and different size. We have corresponding parts. We can see that AB and DE are corresponding. What AB is kind of the same as DE, just smaller. And then BC would correspond to EF. And finally, AC would correspond to DF. And we can use those corresponding parts to find missing side lengths when we don't know them. Here's an example of what I mean. So we have these similar triangles, ABC and DEF. We're given the side lengths in A as being 5, 7, and 10. We're only given one side length in DEF. It's that EF is 11. That's the only one we know. And our job here is to find the length of side DE. Because we have similar triangles, we're going to be able to set up a proportion to solve this. And here's how we're going to do that. We're going to take a look at what we know. What we know over here is this 11. That's going to be an anchor point for us. That 11 is going to be really important. And we find the corresponding part in the other triangle, and that's this 7. And so what we can do is we can set up this ratio that 7 in the small triangle corresponds to 11 in the big triangle. With that in mind, I want to use that same logic to say, all right, I was asked to find DE. That's this side right here. DE. I'm trying to find that. I'll call it X. All right. So what I need to do then is I need to look and say, okay, what corresponds to DE in the triangle that I do know something about, and that's AB. And so I've got this relationship here between 5 and the one I don't know. I set up a relationship at the beginning that said 7 in the little triangle corresponds to 11 in the big triangle. What I want to do is the exact same idea to help me find this X. And what I'm going to set up then is, okay, so that'll be 5 in the little triangle corresponds to X in the big triangle. We have to be really careful when we set these up that we're being logical about it. What I've done here is I've set up, okay, so 7 in the little triangle corresponds to 11 in the big triangle. So 5 in the little triangle corresponds to the thing I'm trying to find in the big triangle. Notice I have little to big, little to big. I have to make sure that the way I set up my proportion makes sense. We can't just put the numbers anywhere we want to. We have to set them up in a way that makes sense. If you had done big triangle over little, that's okay. You just have to make sure you do big triangle over little for your other fraction. Either one of these will give you the same answer, and we'll do it both ways so that you see it. Now to solve this, we're going to cross multiply. 5 times 11 is 55. 7 times x is 7x. And let's see, I'm trying to get x by itself. What do I need to do to get x by itself? Excellent, Jenny. Divide by 7 on both sides. Outstanding. So I'll divide by 7 over here because those will cancel. I'll divide by 7 over here. And then what that leaves me with is everything's gone but the x. That's exactly what I wanted. And on the left-hand side, I'll have 55 divided by 7, which is 7.85714, and that keeps going. Well, I was told to round to the nearest tenth, so let's do that. So we will find the tenths place. That's just 1 past the decimal. I'll look 1 space to the right. Since that's 5 or bigger, we're going to round this up to 7.9. Rounding down would have been 7.8. Rounding up is 7.9. Just to kind of show you that it would get the same thing over here. If I do x times 7, that's 7x. 11 times 5 is 55. And sure enough, we have 7x equals 55. We'll divide both sides by 7 and get the same answer. There's not just one correct way to set up your proportion, but you have to make sure that your logical comparisons make sense. Little over big, make sure you do little over big. If you do big over little, that's okay. Just make sure you do big over little in the other one. Any questions about that before I have you try one? Awesome. Here goes. We have these similar triangles, ABC and DEF. We know those side lengths. What I want you to do is find the length of DF to the nearest hundredth. I'll set up a poll for this one. So the idea here is find our corresponding parts, set up a proportion, and then solve that proportion to find out the length of DF. We'll go another 20 seconds, and then we'll talk about it. If you want more time, you can let me know. Okay, let's see where we are. Not unanimous, but strong agreement. That's a good thing. Not everybody did this. That's either a really good thing or maybe not such a good thing. We'll find out. You let me know if you see anything that doesn't make sense as we go through this. So the proportion I'm going to set up, I only know one side length in the big triangle. So that's kind of my anchor spot. That's critical to me. And I look back over on the small one and I find the corresponding part. And so I know I'm going to use 7/11 as one of my two fractions, one of my two ratios. So 7 is to 11. It's kind of an analogy type of thing for those of you who like English. 7 is to 11 as, and now I have to figure out, okay, DF is the one I'm looking for, so that's here. I don't know what that is. I'll call it X. I need the corresponding part. That's this 10. So I have 7 is to 11 as 10 is to X. So 7 is to 11 as 10 is to X. Keep in mind here, what I've done is I've set this up with little triangle, big triangle, little triangle, big triangle. So that my two fractions made sense. My proportion that I set up made sense. I didn't just randomly put the numbers in. I made sure that there was a logic to it. Now we'll solve this by cross multiplying. 11 times 10 is 110. 7 times x is 7x. We'll need to divide both sides by 7 in order to get x by itself. Divide by 7 on the right, divide by 7 on the left. When we do that, these 7's cancel, leaving just the x. That's where we were trying to get to. And then 110 divided by 7 is 15.71428, and that keeps going. We don't need to write down the whole thing. We're rounding this to the nearest hundredth. So what we're going to need to do is find the hundredths place. That's 2 past the decimal. Look one space to the right. If that's 5 or bigger, we'll round up to 15.72. Since it's 4 or lower, we're going to round this down to 15.71. Hopefully that all made sense every step of the way. If not, if there's any numbers in there, any processes in there that you're not sure where they came from, don't hesitate to ask. Throughout the class, I'll say that over and over again. Chances are, if you have a question, somebody else has the same question. Don't be shy about asking. Don't be hesitant about asking. If we all knew it all, we wouldn't have to come to class at all. So please don't hesitate to ask questions when you have them. And chances are, if you have a question, somebody else has it too, so you're doing them a favor. All right, here's another one. A 3-foot tall dog casts a shadow that is 8 feet long. At the same time, a tree casts a 30-foot long shadow. How tall is the tree? Now, you might read the top of this and say, what does that have to do with triangles? And here's what it has to do with triangles. The words at the same time in here, those aren't meant to throw you at all. It's not meant to be tricky at all. What those are is they're just telling us that the sun is up here in the sky at the same position for the dog and the tree. So it's the same time of day, same location. What that does for us is this. You don't have to draw a picture of this, but I like drawing pictures. On Tuesday of next week, you'll see that drawing pictures will be really important for us. I like drawing a picture anytime we can. Does not have to be a work of art. Here I've got my 3-foot tall dog and my 8-foot long shadow. And if you're thinking, well, where's the triangle? Well, you can kind of see it there that, if I just sort of connect the dots here from the sunlight, that I get a triangle. It's a right triangle with the dog and the ground, and I've got this triangle, and there's my triangle about the dog. Now, at the same time, the sun is coming down on this tree. And it says in the problem that the tree casts a 30-foot long shadow. One thing I will say when we solve word problems, and we'll do a lot of them, and I don't want you to be intimidated by that. I don't want you to be afraid of that. What you'll find is we'll read the problem over and over and over again to get all the information we need. We read it at first. 3-foot tall dog casts a shadow that's 8 feet long. At the same time, a tree casts a 30-foot long shadow. How tall is the tree? Just to sort of get an overall understanding. And then we read it over and over again. Okay, 3-foot tall dog, 8 feet long shadow. All right, I'm going to make a picture of that over here. And then at the same time, the tree casts a 30-foot long shadow. How tall is the tree? So how tall is the tree? That's the thing I don't know. That's what I'm trying to find. So I don't know how tall the tree is. I'll call it T. We use X all the time. We can use any letter we want to be a variable. Since it's a tree, I'm going to use T. But I do know that it casts a 30-foot long shadow. And then here again, those sun rays are coming down. If I connect the dots, I've got these two similar triangles here. And I've got a relationship between those triangles. I'm going to set up a proportion and solve. What I've got here in my triangles is, let's see, the only one I know over here is the 30, and that corresponds to this 8. So what I can do is I can use those to set up my proportion. I can say the shadow of the dog, the shadow of the tree. And then for the other one, I can say, well, now I have the height of the dog and the height of the tree. So height of the dog, height of the tree. And I've set up my proportion so that I can solve it. What I've done here, and again, I want to make sure I'm logical about what I set up. I have the shadow of the dog over the shadow of the tree. And over here, I have the height of the dog over the height of the tree. I don't want to just take those 4 numbers and randomly put them in spots because then it'll get goofed up. For example, if I were to switch these and have shadow dog, shadow tree, height dog, it's going to get goofed up and I won't be able to get the right answers. So you can't just put them wherever you want. There needs to be some sort of logic to the way that you set up your proportion. Now we'll solve this. Cross multiply. 3 times 30 is 90. 8 times t is 8t. And now to get that t by itself, we're going to need to divide by 8 on both sides. On the right-hand side, those 8's cancel, leaving just the t. On the left-hand side, we've got 90 divided by 8, which is 11.25. I was told to round to the nearest hundredth. Well, you know what? This one already is. So that's it. How tall is the tree? It's 11.25 feet tall. Please let me know if you have any questions about anything that we just did there. The idea that how does this make similar triangles is an interesting one. But basically, we knew 2 of the side lengths of the triangle, and we just connected the dots to get the third side. Because it's at the same time of day, the angle of the sun is the same. That's how we wind up with similar triangles. So with triangles, what we talked about was, we talked about properties and definitions. We talked about perimeter and area. And now we've talked about proportions and similar triangles. Does anybody have anything that they want to ask about what we've covered so far before we move on into dimensional analysis? Awesome. Fantastic. If you change your mind, just let me know. All right. So dimensional analysis. You may have seen dimensional analysis before, and it sounds like a big fancy word, dimensional analysis. Really, we're just converting units from one unit to another. That's what we're going to do. When we do dimensional analysis, we are going to convert one unit into another. You may have done this in science classes before, especially a chemistry class. And essentially what we're going to do here is we're going to use something called a unit fraction or several unit fractions to help us convert from one unit into another. Here's some examples of unit fractions. Basically, what we do when we set up a unit fraction is there's a 1 involved, one single unit, like that 1 mile, and 1 mile is the same thing as 5,280 feet. Now, because 1 mile and 5,280 feet are the same, the numerator and the denominator in this fraction are equal to each other. When we set up a unit fraction, that's always going to be the case. These two things are equal to each other. They just use different units. Another example of a unit fraction might be the fact that there are 12 inches in 1 foot. Here again, 12 inches, 1 foot. They mean the exact same thing as each other. It's just they're in different units. And then going between metric and standard English units, we could say that 1 inch is the same as 2.54 centimeters. Here again, our numerator and our denominator are the exact same thing as each other. They just use different units. And what we're going to do is we're going to use these unit fractions or unit fractions like these to convert one unit into another. Let's look at an example of this. And you feel free to let me know if you have any questions about it at all. This is something that a lot of students come into Math 120 having seen before, 120E, coming into the course having seen this before and maybe struggled with it a bit. If you did great with it in a previous course, that's awesome. If you struggled with it before, we're going to try to make it so that you master this. Use the fact that 1 inch equals 2.54 centimeters to convert 40 inches to meters. All right. So what this problem wants me to do is to convert 40 inches to meters. So I'm going to start out with inches, and I need to end up with meters. One thing that's not given to me here is I can see I've got something with inches and centimeters. I don't have anything that gets me all the way to meters. We'll talk about that in a couple of minutes, I promise. The key here, a lot of times with problems like these is I don't even know where to start. Okay, let's fix that. So I'm supposed to convert 40 inches to meters. So I'm starting with 40 inches. That's the thing I'm supposed to convert. So that's where I start. I start with the 40 inches. And I'm just going to write that down over here. 40 inches. The process we're going to use involves a scaffolding for this, where we just sort of set up a structure like that. It may start to feel a little bit familiar. All we're really doing here is making a numerator part and a denominator part for any fractions that we're going to use. We've got a numerator that's going to go up here and a denominator that's going to go down here. That's all we're doing with this scaffolding, is creating a place for our numerator and denominator to go. I need to end up with meters. I'm told I'm supposed to use this fact here that 1 inch is 2.54 centimeters. So basically what that's going to do for me is that's going to take me from inches to centimeters. So I'm going to use that unit fraction, the idea that 1 inch is 2.54 centimeters. I'm going to use that. And I'm going to take this unit fraction and I'm going to write it over here. Now the question is, do I want inches to go on top or do I want centimeters to go on top? And you can think about that. And if you know for sure which one goes on top, you could tell me which one of those is going to go on top. But if you don't, that's all right. I'll give you a chance to tell me if you know, because that's awesome. Okay, inches on top, inches on top. All right, So let me write this down. Don't write anything yet, just follow along for a minute. So I have this unit fraction of 1 inch is 2.54 centimeters. And if I put it with the 1 inch on top and the 2.54 centimeters on the bottom, now the units that I have, when I go to multiply these, I've got inches times inches, so I have square inches on top and centimeters on the bottom. What I was hoping to do is convert from inches to centimeters, and that didn't work. So you know what? Instead of putting inches on the top, let's try the other way. And it's not that we're doing this at random. We're doing it intentionally. I've got this inches here that I want to cancel. I know that 1 inch and 2.54 centimeters are the same. If I want this to cancel, when I write my next unit fraction, I want to put that 1 inch on the bottom and the 2.54 centimeters on the top. And it's not random and it's not guessing. It's 100% on purpose, because what happens now is these inches and these inches cancel, because one's on the top and one's on the bottom, so they cancel each other out. And now all I have are centimeters. I want the inches to cancel, so when I look at this unit fraction, I make sure to put the inches on the bottom. That's how I'm going to get these to cancel. So there's no guessing, there's no random. It's 100% purposeful that I'm going to write down 1 inch and 2.54 centimeters. I just have to decide which one goes on top and which one goes on the bottom. And the one that goes on the bottom is the one that's over here, because I want those to cancel. Let me know if that doesn't make sense. Hopefully it does, but if it doesn't, you can absolutely ask about it. Dimensional analysis, like I said, this is something that students typically, or often, let me change that to often, tell me that they struggled with in the past. And we're going to try to fix it. All right, now I have 2.54 centimeters, and that's great. I used to have inches, now I have centimeters. I'm trying to get to meters, though. And something that you might know, you might not be that comfortable with the metric system, you might be comfortable with the metric system, is that there are 100 centimeters in 1 meter. There's 100 centimeters in 1 meter. So if I want to go from centimeters to meters, I need to use this fact also. So in addition to this fact, I'm also going to use this fact over here. And I'm going to use that unit fraction, that 100 centimeters and 1 meter are the same as each other. And now my question to you is this. I'm going to have to write down 1 meter, 100 centimeters. Which of those is going to go down here? The meters, the 1 meter, or the 100 centimeters? Which one's going to go here? 1 meter or 100 centimeters? Excellent, Jenny. Very good. If anybody doesn't understand why, you can ask it, but Jenny's exactly right. I'm going to put my 100 centimeters down here and my 1 meter up there. And the reason that I put them in those places, it's not random, it's not guessing. It's I have centimeters here that I need to get rid of. So I need to put centimeters on the bottom so that those will cancel. And now my units, the only units left are meters. That's what I was trying to get to. That means I'm done with all my unit fraction stuff. I started with inches. I used this unit fraction to convert to centimeters. And then I used this unit fraction to convert to meters. Meters is where I was trying to get to, so that's all the steps I need. Once I get to this point, now I need to multiply everything that's in the top together. So we're going to multiply all those together, and that'll be 40 times 2.54 times 1. And that's 101.6. And I do have units up there, those meters, so they come along for the ride. The meters that are here come along for the ride. And I do the same thing in the bottom. I look at the bottom and I multiply everything I have down there. This is just 1 times 100. All the units are gone. So the only thing left down there is 100. And so the only thing left for me to do now is just divide those two numbers. 101.6 divided by 100. And I end up with 1.016 meters. This problem told me to round to the nearest thousandth. It's not that often that we round to the thousandth, but here we're told to, and that's 3 places past the decimal, and that's what I've got. So 1.016 meters. 40 inches is the same as 1.016 meters. And that's dimensional analysis. That's what we do. We take unit fractions that we know and we use those to convert our units to what we're trying to get to. Are there questions on that before I have you try one? All right, let's see how this goes. Like I said, sometimes students struggle with these. I'm hoping that you're not going to. We'll see. Use the fact that 1 kilogram is 2.2 pounds to convert 165 pounds to grams. And I'm going to give you one other unit fraction here that might come in handy, that there are 1,000 grams in 1 kilogram. All right, now I'll set up a poll for this and let you try it. So you'll set up your scaffolding, starting with 165 pounds, and use unit fractions to turn that into grams. This is one of those problems that I definitely want you to try it because I want to see where you're at with this. And so not only the feedback for you, but there's feedback for me involved in this one. Well, I guess it's true on any poll, but I'm especially interested in this one because, like I said, there are historically, some students have told me that dimensional analysis was a difficult topic for them. So I want to do what I can to make it comfortable for you. As always, it takes practice. Like we talked about on Tuesday, math is a learning by doing activity. But I want you to feel like you're pretty confident when you do start to practice rather than feeling like you're flying blind. I'm thinking we'll go maybe another 45 seconds on this one. And if you want more time, you can let me know. Okay, let's see where we are on this. Not unanimous, but strong agreement. That's good news. Although there were some of you that didn't submit an answer on this one. One thing I should say, we're pretty early on. If you solve a problem and you don't see your answer listed, that can happen sometimes when we do polls. You work it out and you don't see your answer anywhere on there. Pick the one that's closest to yours. That way I'll know you've had enough time to solve it. So going forward, if you don't see your answer listed, pick the one that's closest to yours. That way I'll know that you've had enough time to solve it. So let's take a look at this one then. So what we've got here is we're supposed to convert 165 pounds to grams. So we start with 165 pounds. What we're going to do is we're going to use unit fractions over here to convert that to grams. The first unit fraction we'll use, well, let's see. I need something that has pounds in it. I know this and I know this. One of those has pounds in it. That's this one here. So that's the unit fraction I'm going to use. 1 kilogram is 2.2 pounds. Because I want pounds to cancel, I'm going to put the 2.2 pounds on the bottom and the 1 kilogram on the top. If you don't understand why a number got put where it put, please ask. I'm positive that you're not the only one with the question. The reason I put the pounds on the bottom is because now these pounds cancel because I have one on top and one on the bottom. They cancel. And the units I have now are kilograms. If I was asked to convert those to kilograms, I'd be done with the unit fractions. Now I'd just do the multiplying part and finish it up. But I wasn't. I was told to convert to grams. So I have to keep going. Right now I have kilograms and I want it to be grams. So I need to find something that'll help me turn kilograms into grams. And that's this relationship right here. And I can use that as a unit fraction. I have 1,000 grams and 1 kilogram. Well, because I have kilograms on top, I need to put this 1 kilogram on the bottom and the 1,000 grams on top. The reason I do that is I want these kilograms to cancel. If I had done it the other way, if I just said, okay, well, I'll put my 1 kilogram up here and my 1,000 grams down here, and now nothing cancels. That's no good. Now I have kilograms twice and grams down here, and well, that's certainly not what I was trying to get to. I wanted it to cancel. So rather than put the 1 kilogram on top, I'll put that 1 kilogram on the bottom and the 1,000 grams on the top. These cancel. And let's see, I was supposed to convert pounds to grams, and grams is what I've got. So I don't need to do any more unit fractions. Now I'm at the part of the problem where I can multiply 165 times 1 times 1,000. And I get 165,000. And I do have a unit up there. I have those grams. On the bottom, I have 2.2 times 1. Well, that's just 2.2. And all the units have canceled, so there's nothing left. Perfect. That's exactly what I wanted. I wanted to end up with grams, and that's where I am. Last thing I'll need to do then is 165,000 divided by 2.2, and I end up with 75,000 grams. That was the most common answer in that one, but if you see something in there that you're not sure why it was done the way it was done, you're not sure where those numbers came from, please just ask about it. We'll make sure we clear it up for you. Okay, one more dimensional analysis problem that I'm going to work for you. This is not going to be a point of emphasis in our class, but I do think you'll see this in the homework this week. Use the fact that there are 5,280 feet in a mile to convert 38 miles per hour to feet per second. So we have this unit fraction here, 5,280 feet in 1 mile. What our job is to convert 38 miles per hour into feet per second. Now, what's new and different about this one is that per in there. It's 38 miles per hour. Per is an indicator of division. And so this 38 miles per hour that I'm starting with, the 38 miles goes on top and the 1 hour goes on the bottom. So we're actually starting with a fraction that has a top and a bottom. We didn't have that before. In our previous questions, it was convert 165 pounds. We started with pounds. We didn't have anything in the denominator. Now, because it's miles per hour, we've got something in the top and we have something in the bottom. It changes our process a little bit, but the philosophy stays the same. Follow along with me here. So I have 38 miles per hour and I'm trying to turn this into feet per second. So what I've got to do by the time I'm done with all this is I need to turn these miles into feet and I need to turn these hours into seconds. So essentially what's going on here is I have two things I have to convert. I have to turn miles into feet and I have to turn hours into seconds. Okay, well, we're going to approach those one at a time. So I'm starting out with miles per hour here. And all right, I know I need to turn these miles into feet. And I've got this unit fraction right here that'll do that for me. 5,280 feet is 1 mile. My question to you is, what's going to go on the bottom? Miles or feet? Excellent, Jessica, Arian, Destiny, Kevin, perfect. Miles go on the bottom. So that 1 mile is going to go on the bottom and the 5,280 feet go on top. And the reason that we put miles on the bottom is the whole reason we were doing this is we want these miles to cancel. Okay, if I were to quit right now, I have feet per hour. Well, I'm supposed to get feet per second. I'm not done yet, but I'm closer. At least now I have feet. Now I need to turn that hour into seconds. And I don't know, you might know how many seconds are in an hour. I have no idea. So I'm going to avoid that. And I'm going to say, well, 1 hour is 60 minutes. So I can use that. I don't know that this is that easy of a question. So I'm going to go ahead and ask it. 1 hour is 60 minutes. That's the next unit fraction I'm going to use. When I put that unit fraction here on my scaffolding, what's going to go up here? Hours or minutes? Be careful with this one. What's going to go up there? Hours or minutes? And it's okay if you're wrong. There's no stakes here. Okay, Jenny says hours. Arian says hours. Nicole, hours. Looks like we're pretty consistent with the hours. Let's see if I agree with you on that. If I put the 1 hour up here and the 60 minutes down here, well, I wanted hours to cancel. Well, look at that. Hours on the bottom, hours on the top. Sure enough, you were all right. Hours goes on top because I wanted to cancel with the thing that was on the bottom. If I were to quit right now, I have feet per minute. Still not what I'm trying to get to. I'm supposed to have feet per second, but I'm closer. I need one more, and I know that there are 60 seconds in 1 minute. And so that's what's going to go on my scaffolding next. And I'm going to put, let's see, I have minutes on the bottom. I want those to cancel. So I'm going to put my 1 minute on the top and my 60 seconds on the bottom. The minutes are going to cancel. And now the units that I have left at this point are feet per second. Hey, that's what I was trying to get to. So now I'm done with my unit fractions. Now I'm finally at a place where I can multiply along here. And let's see what I'll wind up with. I'll get, let's see, 38 times 5,280 times 1 is 200,640. And the units I have up there are feet It's a big number, but we have a calculator. It's okay. And then on the bottom, I need to multiply all those together. And let's see, I'll have 1 times 60 times 60 is 3,600. And the units I have down there are seconds. My units are great. They're exactly what I wanted. Feet per second. The only thing left for me to do here is divide 200,640 divided by 3,600. And it's 55.7333333, and that keeps going. This problem told me to round to the nearest tenth. So we'll find the tenths place, we'll look one space to the right. Since that's 4 or lower, we're going to round this down to 55.7 feet per second. So if you're traveling 38 miles per hour, you're traveling 55.7 feet every second. I think that's a pretty challenging question, but please keep in mind that the philosophy is the same. What I mean by that is we use a unit fraction, we set it up in a way that the units we want to get rid of will cancel. And then we do that again. And then if necessary, we do that again until eventually we get to a place where the only units that remain are the ones we want. And once that happens, then we're done with the unit fractions.